In section 4.4, we talk about the fundamental theorem of calculus. So far in this chapter, we've explored two main concepts, antidifferentiation and definite integration. These two concepts, although they may seem similar, they are very different because antidifferentiation is just a family of functions which are considered the original function for small f of x, whereas the definite integral is just a number because we are trying to evaluate the limit of a sum at infinity. So we are trying to find a number. However, in this chapter, we see that these two concepts are similar, and that's the reason why they have the same symbol. And that's what the fundamental theorem of calculus says. It says that if a function f is continuous on the closed interval ab, and f is an antiderivative of f on the interval ab, then we can rewrite, or the solution for the integral of f of x from a to b is just the antiderivative at point b minus the antiderivative at point a. And once we have this theorem here, it becomes simpler to find any integral, any definite integral, because it would be simpler to find the antiderivative of function f instead of computing the limit of an infinite sum. So now, in order to find to apply the fundamental theorem of calculus, first we need to provide an antiderivative for the function f. For instance, if we have the integral from a to b, if we have the from a to b of let's say 3x squared, first we need to find an antiderivative for 3x squared, that would be x cubed in our case. We can just find the value of x cubed at point b, and then the value of x cubed again at point a, and then we can just do the difference between the two, and we'll end up finding the definite integral. When applying the fundamental theorem of calculus, it's not necessary to include a constant c. Why is that? Because it will be removed, because we'll need to have a constant c for f of b and another constant c for f of a, and with a minus here, the two constants will eliminate each other, and we'll just have f of b minus f of a. So when solving the definite integral of f of x from a to b, you don't need to add a constant. So let's try to solve this definite integral here. So we have the integral from 1 to 2 of x squared minus 3 dx. First, we need to rewrite this as x squared dx minus the integral from 1 to 2 of 3 dx. Then the antiderivative of x squared is just x cubed over 3. So we can come and then have this. Then we can use this symbol here to represent that we are trying to find the values of x cubed over 3 at both 2 and 1. We can do the same here, since the antiderivative of 3 is just 3x, so we can take 3 outside, and then we just have x, then we have here 1, and then 2. This will lead to x cubed over 3 at point 2 will just be 2 to the power of 3 over 3 minus 1 to the power of 3, which is just 1 over 3, Then this is the first part. Then we'll end up with just minus 3 times 2 minus 1, which is just 1. Or we can write 2 minus 1. This will end up being 8 over 3 minus 1, which is 7 over 3, minus 3 times 1, which is 3. Then this is just going to be minus 9 plus 7, just minus 2 over 3. Section 4.2, we saw that the area under a curve, which is this, is bigger than the rectangle. The area of the inscribed rectangle, and it's smaller than the area of the circumscribed rectangle, which is this. However, you should also note that between these two rectangles here, there should be a point somewhere between A and B where the rectangle, the area of the rectangle will be equal to the area under the curve. You can see that in here in this example because we'll end up, this is the area under the curve that is covered by the rectangle plus an additional area here, which is not the area under the curve. However, if we look at this area here that is not covered by the rectangle, these two areas here are equal. So we can assume that the area covered by this rectangle here is equal to the area under the curve. This is the value for that area. The area of the rectangle will just be f of c, which is in this case the height, times b minus a, which is the width of the rectangle. And that's what the mean value theorem states. It says that if a function f is continuous on the closed interval ab, then there should be a c in ab such that this equality here is correct. This equality here will be correct because the definite integral is just the area under the curve f of x, and this here is also an area. And we just saw that f of c times b minus a is the area of the rectangle. Is the area of the rectangle for which it is equal to the area under the curve. And that's what the mean value theorem says. Another important concept in chapter 4 is the average value of a function on an interval. So they say that if a function f is integrable on the closed interval ab, then the average value of f is just this value here. First, what is the average value of f? So let's take this function here. Let's say that we have this function, this is f. So, and this is a, this is b. So what we mean by the average value of f is just that we want to find what is the average value of f. Let's say that this is x2 and so on. So what we want to find is just the sum f of x1 plus f of x2 plus f of x3 plus all the way to f of xn, where xi and from x1 to xn, they are all in AB. And then we need to divide this whole thing by b minus a. It's like we want to find what is the average or the average value of f on this interval AB. And that average value is what we were given. It's just 1 over b minus a, the integral from a to b f of x dx. So if you were ever asked to find the average value of function f, you just use the definite integral and then you divide by b minus a. We always had a and b, which are constants, as the limits of our integration. But now what if we change the upper limit, which is b, to be a variable x? Then we'll end up with a definite integral, which is a function of x. Why is that? Because according to the fundamental theorem of calculus, if we were to compute the derivative or the integral of f of t between x and a, we'll end up with f of x minus f of a. Or okay, you can discard this. And this will be a function of x because we'll have f of x, a function of x, plus a constant, which is the whole thing will be a function of x. And now, if we were to differentiate this function here, once again, we'll end up with, if we were to do d over dx of the integral from a to x of f of t dt, we'll just end up with, so if we were to replace this with this function here, so let's try to differentiate this part, we'll end up with f of x prime minus f of c prime. This will be a constant, so it will go because it will be 0, and we'll end up with just the derivative of f of x here, and the derivative of f of x is just small f of x. Then this means that if we were to differentiate this function here, so if we were to do the derivative of this function here, it will just be f of x. And that's what the second theorem of calculus states. It says that if a function f is continuous on an open interval I containing a, then for every x in the interval, the derivative of the integral will just be this function here, and then we replace t with x. Let's look at an example. So let's try to evaluate the derivative of this function here. So first we need to check whether t squared plus 1 is continuous, because one of the conditions for to apply this theorem is that f needs to be continuous on 0x. So let's t squared, we have t is greater than 0. Then this means that t squared is also greater than 0. It also means that t squared plus 1 will be greater than 1. Then the square root will also be greater than 1. Then this function here is continuous. Then this also means that if this function is continuous, then we can find the derivative easily by just replacing t with x. This means that the derivative of the integral from 0 to x of the square root of t squared plus 1 dx will just be the square root x squared plus 1. What this theorem says is something that we've already discussed when talking about the second fundamental theorem of calculus. It says that if we were to integrate from a to b, f prime of x, we just end up with f of b minus f of a. First, what is f prime of x? F prime of x is just f of x, because we know that big F of x is just the antiderivative of small f, and f is just the derivative of big F. So if we were to differentiate the big F of x, we'll just end up with f of x. And then this is the same as writing an integral from a to b of f of x dx. And using the fundamental theorem of calculus, we found that this is equal to f of b minus f of a.